Now, is a next speaker is Pierre-Marie. It's about have astronaut assigned a signal produced by the ocean to the cosmos. It sounds very exciting. Okay.
Can you hear me? Yeah. So I'd like to start by dedicating this talk to my oldest son, Jacob. And so what I'm talking about is, as most people here know, that mankind believes that we've measured the microwave background of the universe, and we've set a temperature of it of 3 Kelvin degrees. And of course, when you make such a measurement, you think, well, there can be nothing here on Earth at 3 Kelvin, so this must come from the universe. And so if you look at the very first finding from the famous paper by Penzias and Wilson, they find a background temperature of around 3.5 Kelvin, which was isotropic, unpolarized, and free from seasonal variation. So how could it be that this can possibly come from the Earth, right? And they immediately, at the end of their paper, it's interesting that this paper was actually interpreted before the result was published. So this paper, the paper by Dike, actually precedes the Penzias and Wilson paper. So it's something quite unusual in science that you interpret the paper before you even present the data. So we've thought that this monopole, which this was measured by the COBE satellite, so around the Earth, we're embedded by this microwave signature. And now, sometimes I'm going to use terms that might be a little difficult for people, and I'm sorry about that. But this is the monopole is just the blackbody signature itself, and it represents the most perfect blackbody radiation curve which has ever been measured. I guess I made a mistake. I'm supposed to stay here. So it represents the most perfect blackbody radiation curve ever measured. And but yet the monopole has actually never been recorded away from the Earth. So if you go 1.5 million miles away from the Earth at L2, you get anisotropy maps there, which I'll show on the next slide, but we don't cover the monopole there. The signal to noise on this plot is so high that the error bars are buried in the line width. So this is like, it's not only the most perfect blackbody ever measured, but it's phenomenal signal to noise. You have to blow up the error bars by a factor of 400 just to see them. So, however, there's a rule in radio transmission. I don't know if some of you guys are amateur radio operators. I am. And there's a real rule in amateur radio that if you have a strong signal, you're close to the source a lot of times. And that's especially true when we're listening to our radio stations, local radio stations. And there are anisotropy maps that have been measured by both the WMAP and COBE and Planck satellite. And these were measured at L2, 1.5 million kilometers from the Earth. And I've written a paper analyzing these maps. The first thing is you see the red band there at the bottom. That's the galaxy. So the astronomers are trying to make us believe that they can look through the galaxy and extract a small residual signal from behind it. And so, first of all, the galactic signal in the microwave is not stable, and it's not stable enough you cannot extract it. And to try to extract the red signal from the map and produce the image at the top is scientifically unjustified. One cannot extract a weak signal from a powerful overlapping signal without a priori knowledge. And anyone who's done this, who knows anything about liquid NMR, just if you have a water line and you have a peak right under it, you'll never be able to extract the peak. It's absolutely impossible. So to try to say that they can generate the image at the top is just, it's not science. So I've written a full paper about WMAP, a radiological analysis. And for those who are interested in this analysis, this is actually an analysis from a radiological perspective. I'm a professor of radiology, and so I'm just looking at the image and how they processed it and the kind of things that they're doing, and you'll see that It's just not science. There's no other. I cannot believe that this has been permitted to be published without comment. And this is part of the problem when you have a large organization and they peer review one another and no one is going back and saying, hey, what did you guys do? And would this pass in human medicine? And of course, in medicine, I do consider that we are the authorities in imaging. If we make a mistake, especially in the United States, physicians get sued. So we have an incentive to get things right. There's also a paper that analyzes the COBE satellite. And there, for COBE, it circled the Earth, and it had a shield around it, and you can get diffraction from an earthly signal over the shield into the Phoeris horn. And even Wilkinson, who is, WMAP is named after Professor Wilkinson when he died, even Professor Wilkinson feared that you could have diffraction across the shield into the Phoeris horn, and that it could be possibly some earthly contamination. If you're interested in more about the analysis of the microwave background and these maps, I gave a talk, which you can find on YouTube. If you just type my name and the cosmic microwave background, you'll get much more information. If you don't want to read papers, I do go through the analysis in detail. So, but yet the monopole is still real. It's clear that it has a black body appearance, which is indisputable, and it reports an apparent temperature at 3 Kelvin. So the first thing, is the temperature accurate? And I will state that the rule in physics, if you believe Kirchoff's law, the rule is that you can take a temperature provided you have thermal equilibrium with an opaque enclosure. Well, the Big Bang was not in an opaque enclosure. So what the astronomers tried to do is they tried to tell us that at recombination, you actually had, for an instant, thermal equilibrium. It's just, you're just reaching. Okay, and has the origin of this spectrum been properly assigned? And I dispute that it has. So if you look at blackbody radiation, just a brief review for people who are unfamiliar with it. In the laboratory, you make cavities and you line the cavity with soot or graphite. This is how they did it in the 1800s when Kirchoff wrote his law. And so you line with soot and graphite, or graphite. Now, when Planck got his results, you actually used the rolled platinum black because in the IR, graphite doesn't do as well. And so you tend to use blacks like gold blacks or platinum blacks for those frequency ranges. But typically, laboratory blackbodies are cavities lined with graphite walls. And this is still the standard today at NIST. Now, so Kirchoff's law says that if you build a cavity like this, within any cavity, the radiation must always be black or normal. It always will have a kind of distribution which looks like these curves, and the temperature of what's inside, the curve shifts according to temperature. And Kirchoff's law says that the shift depends only on temperature and frequency and is independent of the nature of the walls. But of course, I do MRI, and we use cavities. And in communication, we use microwave cavities. And those cavities are resonant. They're not black. So if you look at so Kirchoff is saying within all cavities you get black radiation. And what I'm saying, that's absolutely false. Now, of course, he said this law in 1860, and it was a theoretical law without experimental validation. So when he wrote his paper, there's no experiments in Kirchoff's paper. He just wrote the law, and it was all mathematical. And then all those mathematics have collapsed since 1860. And I think in 1919 or 13, Hilbert, this is well after Planck, gave a lecture, and he said that there's no valid proof of Kirchoff's law. And that's still true to this day. And the reason that there's no valid proof is, of course, perfect reflectors cannot sustain blackbody radiation. If you have a cavity that's made from something like silver, and you send radiation into it, the radiation will become phase coherent. You build up standing waves, and it doesn't go black. So you have Q values in the microwave. You can have Q values of 10 to the 11th in the cavity. That means for every 10 to the 11th waves that's going back and forth, you dissipate one. Now, with that kind of Q, it's just unbelievable. So this will never be black. So Kirchoff's law cannot be valid. And the reason is, when Planck did his experiment, when Planck wrote his theory, this is the next slide, he failed to link his equation to a physical cause. And this is something extremely important in physics. Planck's law, even though it's so important and is correct in terms of giving us the shape of the black body spectrum, it's actually the only equation in physics which is not linked to a physical mechanism. So this is why astronomy has lost its way, because they can advance anything to produce a black body spectrum. So contrary to all other spectroscopic processes, and I'm a spectroscopist by training, I was trained as a chemist, contrary to all other spectroscopic processes, a setting, a transition species, and energy levels for the transitions are never described by Planck. That's because he says it's independent of the nature of the walls. And Einstein himself spent 5 years trying to understand why we get a thermal spectrum, and eventually he gave up, calling it a hopeless undertaking. So this is a problem that has still not been solved by physics, even though it's a problem that's 100 years old. So we know Planck got the right equation, but what he does, so to get his equation, he uses oscillators. But then he tells us, well, it's independent of the nature of the walls, so he doesn't want to give us the cause, and a physicist is not allowed to tell us the cause. So we think we understand the universe, but we can't explain why does graphite emit a photon. So the important thing is, for Planck and Kirchoff, all that is required for obtaining a black body spectrum is thermal equilibrium with an enclosure, which of course Penzias and Wilson did not have. So even if Kirchoff was right, he actually still required something. So that's why Penzias and Wilson were not allowed to take a temperature and call it real. To call it real, you must have thermal equilibrium with an opaque enclosure. As a result, the astronomers believe that they can obtain a black body spectrum from phenomena absolutely unrelated to a mechanism used by graphite on Earth. So this is true for the microwave background. It's also true for the sun. In reality, the production of a thermal spectrum requires a structural lattice. So Planck is saying we don't need to have a cause, and I'm saying this is an error because Kirchoff made a mistake. So remember, Planck was trained by Kirchoff, so he believed that Kirchoff was right. His idea that it's independent of the nature of the walls must be true, so therefore physics never linked Planck's equation to the physical world. So I'm saying, and I said in this 2003 paper, so I've been at this a while, that it absolutely requires the presence of a physical lattice. So we have the production requires a presence of a structural lattice, and as a result, the photosphere of the sun must have a lattice. And so I've said that the sun cannot be a gaseous plasma. It actually has to have structure. It has to have a lattice. And I'm saying that the sun is metallic hydrogen, which was compressed in its interior and comes to the surface. And there in the photosphere, the atoms are vibrating, the lattice is vibrating, and this gives us the light. Whereas the astronomers are saying we're going to take a sum of many processes which have nothing to do with blackbody radiation, and we're going to build a blackbody spectrum from it. And this is, again, it's not science. And this is about 100 years of building black bodies for the sun for this way. So I'm saying that the stars are condensed matter. And you can read more about this. Now, how about the monopole of the microwave background? So it also has to come from a lattice. And one thing is clear is it was never one at the Big Bang. We can also talk about the Hawking radiation. So these are all different mechanisms. For the sun, we say that we get the blackbody radiation from summation of many processes which have nothing to do with blackbody radiation, bound, free, and so on, scattering. So is the sum of these processes. For the microwave background, they tell us, oh, it's at the recombination event that we magically get this spectrum. Professor Hawking tells us that in black holes, he gets it from pair production at the event horizon. These are all different mechanisms, all to give a blackbody spectrum. The Unruh effect is an infinite thermal bath, which doesn't even exist in thermodynamics. And so Unruh temperatures and Hawking temperatures will never be real. You must have a lattice. And so now we can fix these two because these are actually real spectra. So it is not possible that this spectrum originated from the universe. The optimum lattice for the production of such a spectrum is shared by graphite and soot, and clearly the Big Bang did not have it. And so water is the likely source. So I've said, I like this quote, but water, water everywhere, nor the drop to drink. So here we're sitting on the Earth. You'll see that there's always problems in the microwave background experiments near the Earth with water. And I just want to cover some examples here, some quotes. When Smoot was building his radiometer, he quoted in his book, "An invisible patch of water vapor drifted overhead. The scanner showed a rise in temperature. Good. This meant that the instrument was working because water vapor was a source of stray radiation." There's Rainer Weiss, and he said, "Temperature, pressure, and constituent homogeneities occur, and in fact are the largest source of random noise in ground-based experiments. However, they do not contribute systematic errors unless the particular observing site is anisotropic in a gross manner because of a large lake or ocean in the direction of the zenith scan, for example." Here's one on John Mather about the problems with the Atlantic Ocean. He's talking about another group. "Their job was unusually difficult because Atlantic weather creates patterns in the air that can produce signals similar to cosmic fluctuations. It took the English scientists years to eliminate this atmospheric noise." Here's one from Woody. "On the ground and during the ascent, the antenna was protected from atmospheric condensation by 2 removable windows at the top of the horn. At the same time, a small glass mirror allows us to check for atmospheric condensation in the antenna by taking photographs looking down at the throat of the horn and the cone. So clearly they don't want any condensation. They don't want any water there." Here's one from George Smoot in his book. "It is much more humid in the tropics. As the plane descended from the colder upper atmosphere into Lima, the chilly equipment condensed humidity into water. As a result, water collected into the small sensitive waveguide that connect the differential radiometer's horns to the receiver. We had to take the receiver apart and dry it. Our experiments had dried, so we reassembled it and tested it, and it worked." Here's another one on condensation. "The effect of air condensing in the antenna were seen. When the second window was open, the valve which controls the gas flow should have been rotated so that all the gas was forced out through the cone and the horn. When the situation was corrected, emissions from the horn were reduced as cold helium cooled the surfaces on which the air had condensed, and the signal returned to normal levels." So they're telling you, my water condensation is going to give us an artifact, right? So the most likely candidates are the oceans of the Earth themselves. So you have to ask yourself, relative to Penzias and Wilson, they're sitting on a water planet, and they get the spectrum immediately from the universe. Where's the contamination from the oceans? There has to be one because water is absorbing in the microwave. So the universe is not contained. These are some objections. The universe is not contained in a rigid enclosure. It had no access to structural lattice at the beginning of time and therefore did not produce the spectrum. The Big Bang is a non-equilibrium process by definition. There never was thermal equilibrium with an enclosure as required by Kirchoff's law, even if the law was valid. And on Earth, the creation of a blackbody spectrum has always required the presence of a vibrational lattice. So when we build blackbodies in the laboratory, we always use things that are very good absorbers of radiation. You don't build blackbodies from silver, which is a nearly perfect reflector. And you do build MRI coils from that, though, because we want standing waves, right? So water is known to be an excellent absorber of microwave energy, as seen in our kitchens and observed in our submarines. So water must therefore be a powerful emitter. So where's the microwave emission spectrum from the Earth? I'm not talking about the atmosphere, I'm talking about the oceans. Why did it not interfere with the Kobe measurements? So if you look here at the water dimer, this is a very simple analysis on the water dimer, which is known to occur in the atmosphere. I'm just using it to talk about the energy. If I have these two bonds and I characterize them with force constants K1 and K2, and the displacement of the hydrogen atom is either x1 or x2. Well, when the hydrogen atom moves, x1 is just minus x2, and so you can show from this that the ratios of the energies are the ratios of the force constants. So that means that if the bond for the force constant is about 100 times stronger for the hydroxyl bond than it is for the hydrogen bond, so as a result, the energies will be about 100 times different. So if you have a 300 Kelvin signature from the hydroxyl bond, you can get a 3 Kelvin signature from the hydrogen bond. In order to obtain a thermal spectrum, it takes more than the ability to simply absorb and emit microwaves. The material must also emit at all frequencies, and that's why you need the required structural lattice. So if you look at graphite and soot, they're unsurpassed in their ability to act as natural black bodies in the optical range. And this is in part a result of electron delocalization over these ring structures, which enable the conversion of vibrational energy to light and vice versa. So even it's amazing that even a single layer of graphite is an amazing absorber. Just one layer, it absorbs 2.3% of the incident light. So in graphite, each carbon is sp2 hybridized and is bonded to 3 other carbons, and 1 electron is then placed in each p orbital, which then can be delocalized over the structure. Of course, in ice, the hexagonal structure is present, but it's not planar. The electrons cannot be localized over the rings for strong absorption in the optical range, as seen in graphite and soot. It's clear you don't have that. But people here know that there could be a hexagonal planar structure in water. And the idea that liquid water can adopt a hexagonal lattice structure at interfaces has been largely dismissed by the scientific community. And this is the classic paper that disagrees. And if you look at modern textbooks on the hydrogen bonding in water, they'll never mention this structure. So this is a classic book by Maréchal, The Hydrogen Bond and the Water Molecule. It's a pretty recent book. It's a good book, but you won't see anything about a planar structure of water. And of course, all of you guys know about Jerry's book. So we talked about graphite, how it looks, and this is how water will end up looking with the hydrogen in between the 2 oxygens there. So the distance between the p orbitals is much too great to have resonant structures in the optical. But what if the hexagonal planar structure lattice of water, which might exist at the surface, is compressed, and one might expect excellent absorption in the optical as electrons become delocalized and bond lengths are shortened? Can the surface of water become optically black on compression? So this is the question, right? If we think we have hexagonal planar structure, can we make it optically black? And the answer is yes. So this is a sad thing in history that we ever did this, and every time I show it, I always regret that I have to talk about nuclear explosions because it's so tragic that man did it. But nonetheless, as a scientist, you look at the data, and a professor years ago had asked me to read this book, and he was an old professor, and I really loved him, so I decided, even if I was an MRI guy, I would read this book because he had been his whole life working on nuclear problems, and he wanted me to read this book, The Effect of Nuclear Weapons, which I can tell you is a sad read. But in this book, years ago, 20 years ago, long before I became even aware that there was a microwave background, because when I was doing MRI, and I had no idea that mankind had claimed such a thing. And I guess it's the sheltered life of being in a medical school. In the course of so this is what it says in this book. What happens now, so this refers to a shallow underwater explosion, and as happened with the Baker explosion in 1946. And the bomb at that point was 90 feet below the surface of the water. It was suspended under a ship, and the water depth was 180 feet. So 90 feet under, and then the bomb went off. And so this is what it says. In the course of its rapid expansion, the hot gas bubble, while still underwater, initiates a shock wave. intersection of the shock wave with the surface produces an effect which, when viewed from above, appears to be a rapidly expanding rim of darkened water. This is often called the slick because of its resemblance to an oil slick. So now I'm going to show you a video of this explosion at Bikini Atoll. A very sad story, by the way, because the king of Bikini Atoll gave the U.S. government permission to do these experiments on his land. So you see it there. It's very quick. And I'll repeat it in slow motion. So it's not that the water is coming, it's not becoming black because of something below the water. You'll see that that's being shot up into the water. It becomes black, and then it becomes white. So first, there's the slick, and then there's something called cracking. So there it goes, it's starting to go black, you see it, and now it's going to crack and become white, okay? So this is not like pollution from below. The bomb is sitting high, so it's the first shock wave that's going through the water. So these are experiments we don't want to repeat. And this video is available from the U.S. National Archives. Anyone is welcome to use it and display it. And this is another video of the same thing, but viewed from the shore. The sun is behind the palm tree. So it's not, what you're going to see here is not a shadow. This is the same explosion. All right. So there's really the sickness of man in all this. So you see the shock wave come, and then you'll see the palm tree move. Oh, I guess not in the slow-mo one. My son prepared these for me. My son Luke, my youngest son. All right. So it's interesting, if you look at the emissivity of water, water is actually transparent at shock pressures under 300 gigapascals. And I think this might be a Russian group. But you can, anyhow, this is known to be transparent. But if you shock compress water between 50 and 80 gigapascals, then you get this phenomenal finding. Within the accuracy of the data, shocked water in the pressure range of 50 to 80 gigapascals radiates as a black body with an emissivity of 1. That is just amazing. Okay? So you get temperatures of 3,300 to 5,200 degrees in water when you shock compress it. So what's happening now? You've got this ring, and you're shock compressing it. So now you had a non-resonant structure in the optical, and when you compressed it, now it became resonant in the optical, so now it can absorb the light. But in order for this to happen, the structure must already be there. So this is the point. This is, I always say, don't use neutron diffraction. It's too violent of a method. And yet I'm using nuclear weapons to tell you how it's crazy. So what is happening? The shock wave is moving rapidly through the water. The molecule doesn't have time to move and change its structural organization. So now, because the shock wave is happening so fast, now it's becoming optically black. So that means that the structure had to be there before. So for what I'm trying to tell everyone in the room is this provides evidence for structure in water on the surface. There's another thing that's very interesting about water is that the brightness temperature of the horizontal component of water increases with wind speeds. It goes from 82 Kelvin at a wind speed of 0 to 98 Kelvin at 14 meters per second. So wind affects the brightness temperature of water. So in conclusion, it's impossible that the monopole signal from the microwave background originated from the universe. So how do we correct this? Well, the first thing the physicists have to do is we have to link Planck to a physical cause, right? So if you have a Lyman line in spectroscopy, and I have a Lyman line from a proton, okay, why do I get the Lyman line from a hydrogen atom, right? It's an electron, and it's doing a transition from the second energy level of the electron to the first energy level. So this is the two energy levels, and the transition species is the electron, and the setting is the hydrogen atom. So we have to define now for Planckian for blackbody radiation what these three things are. What's the setting, and what are the energy levels, and what's the transition species? And once we do that, once we say, hey, if you want blackbody radiation, you must have a lattice, then what happens to astronomy? It collapses. Because everywhere in astronomy, they assume that they can get blackbody spectra without having a lattice. So this is a problem for condensed matter physicists. As soon as condensed matter physicist says, if you want a blackbody spectrum, you must have a structural lattice, then it's over. All these ideas collapse, gaseous suns, black holes, all this is just... So anyhow, it's impossible that the microwave background originated from the universe. Water has the ability to absorb and emit in the microwave. So where is the Earth's signal? Optical measurements of water during soft compression demonstrate that water has the ability to absorb much like graphite in the optical range with the phenomenal emissivity of 1. As such, the surface of the oceans are very likely to possess a hexagonal planar structure as proposed by Lippincott and now by Professor Pollack. The oceans of the Earth are likely to have at their disposal the physical ability to produce a thermal spectrum in the microwave, which can fully account for the monopole signal of the microwave background. So I would like to thank everyone for listening, for my son Luke, which helped me with... Luke is always helping me. I've been blessed with 3 sons, and he's always my buddy and helping me whatever I need. And then Professor Robert Bailey, he's an old man now. He's 90 years old, but he's the one that made me read that book years ago, which I never realized I would someday need that book so much. And you talk about a super nice guy is Professor Bailey. And Bernadette Carstensen is an artist and just a wonderful artist. If you ever care to look at her website, the kind of drawing she did the drawing of Max Planck. And you can learn more on my video channel, which is quite controversial, but you know, the astronomers are telling us that the sun is a gas, so therefore it doesn't have a surface. And I'm saying, no, the sun has a surface, and there's much, much evidence for it. We have transverse waves on the surface of the sun, and you don't get transverse waves in the gas. So if you start looking, and it's just a matter of saying, oh, no, there's a surface here, and it's real. And so if you look at this channel, you will see much, much evidence of the sun being condensed matter. I also discussed the laws of thermodynamics, which I encourage everyone to always remember that they're real and extremely important to science. God bless you all, and thank you for listening.
Thank you very much for this absolutely interesting presentation. I learned a lot today about nuclear explosion, of course. Okay, questions, please.
Thank you. Mind-boggling. 3 questions. Question number 1 is, you probably then, if I use Michio Kaku's hypothesis on the grand unifying theory based on blackbody radiation, in this case the cosmic background radiation, so it's not valid at all, it's
right.
A theory that crumbles?
Yeah, so it's just like if you look at the cause of the explanation of blackbody radiation and Hawking radiation, a similar thing. And there's like 13 theoretical explanations of why you get a blackbody there. So this is just theory. I mean, what we need is, we need to understand the physical. We do physics, so what is physically happening in graphite? And I don't care what people write in theory. I care about what Planck did. It's very important. I don't mind having a beautiful equation that fits the data. I don't mind that. But when you do just theoretical work to say, I can produce a photon from a pencil, you can't do that. You must put a physical mechanism to the production of the photon.
All right. Okay, this brings me to the other one. Based on the nuclear explosions that you showed us in the slow motion, I mean, you have a propagating, cavitating shock front that's actually propagating through the waterfront at the surface. So you probably have a resonator that, when you induce the cavitation due to the shock wave that comes in,
There is cavitation after.
Sonoluminescence feeding back to the water body, so you have an oscillating standing wave ring propagating outwards into the periphery, right?
Well, I think you do have cavitation. When the shock wave first comes, right, it becomes optically black, and then, of course, now there's compression, and this is going to fall apart. It's going to relax, and you're going to get cavitation, and it all goes white, right? So yeah, I think there's evidence for
this would explain
the cracking, and I think they call it the cracking. Now, I've been looking, and if somebody finds it, why is it called the crack when it becomes white? And I assume it's because scientists heard it crack, the water cracked.
All right, okay.
Okay.
Thank you. And the third one is a little bit more provocative, but based on your, let's say, association between Kirchoff and Planck and this Blackbody radiation equation, which is purely empirical, it reminds me a lot, and maybe you can tell me a little bit more about that. It reminds me a lot about those experiments that Wilhelm Reich did with his organ chamber. So maybe Planck was doing nothing else than just an organ-like experiment.
Well, I mean, Planck never did experiments, but if you look at the work of Rubens, right, they actually built specialized cavities for Planck. I mean, they worked, you know, if Kirchoff was right, any cavity should give you a black-body spectrum. But the reality was that scientists had to work very hard in the laboratory to build the black bodies, which eventually gave Planck the answer. Not all cavities were black. They were structured material, yes. For Planck, it was rolled platinum that made this black body. With a cavity interior, but the walls were rolled platinum, if I remember.
More questions?
Afternoon. I have a friend, she's a disciple of like Schauberger and Theodor Schwenk, and she has an idea that deep water, artesian water, is fundamentally similar to like distilled water, and that surface spring water is much more desirable because it's had the ability to communicate with the cosmos, and the deep water is fundamentally dead with properties and nutritional values. And I was wondering if your research has any kind of...
I don't do research in water. What I care about is black-body radiation, right? This is my central thing. I mean, for this question, you should go to the previous speaker. I think she's more an authority than I would ever be.
Fair enough.
Thank you.
Okay. I think we have to move to the next speaker. My short question, how difficult to get these videos?
I don't know how they did it. But how can you get it? They're everywhere. You can find it on YouTube easily.
Okay.
So I could just tell you in closing, when I first read that book, of course, I gave it back to the professor, right? And then years later, I remembered reading that paragraph in the middle of the book, and I called him up and I said, do you still have that book on nuclear weapons and stuff? And he was old, and he had moved with his wife to a new place. And he said, Pierre, it's in my box. I have no idea where it is, So about 3 years later, or several years later, I called him up again, and I said, Dr. Bailey, do you think you might know where that book is? Because I really needed it now for my science. I needed that quote, that it became optically black. And he says, I just don't know where I put that book on the effects of nuclear weapons. And then I thought, I wonder if it's called The Effects of Nuclear Weapons. So then I Googled it, and that's how I found the book. Okay, God bless you all. Thanks.
Okay, thank you very much again.